All right, so there's an integral form of impulse, and in AP Physics 1, if you did that, or if you didn't learn it, we did F delta T, and we talked about the area under the graph being the impulse. But really, if the force is not constant, just like with work in Unit 3, then the more general form is of the impulse momentum theory is an integral. So rather than F delta T being the area under a graph, you're just going to say it's the integral of F dt. And so that's like so remember that this is a vector though. So when we do this integral, we got to do the x and the y's separately. Okay, we cannot it's not a scalar like it was in Unit 3 when we do work and energy. Okay, so just be very careful when you're doing this part. So we have a time varying force right here. So this is a one-dimensional. It's a force with a constant k over time. What is the impulse applied over the first 10 seconds? So we're just going to integrate f dt, and you're integrating over time, and you're going from 0 to 10 seconds. So it's the integral of 0 to 10 of 4kt squared dt. The 4k is a constant, so you just integral of t squared dt is going to be t cubed over 3 by power rule, and t goes from 0 to 10. So that's going to be 4k over 3, just bring the 3 out, times 10 cubed. Minus, plug in 0, you get 0, so you just get like that. So that's going to be, what, 4,000 k over 3, like that. Okay, let's do one with a vector one. So we have a time-varying force. It acts on what is the magnitude and direction of the impulse applied over the first 5 seconds. So now we're integrating from 0 to 5, but again, we got to do the x and the y components separately. So the x direction, okay, is going to be integral from 0 to 5 of 3t dt, just the x component. And so that's going to be 3t squared over 2 from 0 to 5. So that's going to be 5 squared, which is 20. That's like 75 over 2, like that. Okay, and then in the y direction, got to integrate that. So we're going to integrate from 0 to 5 of 2 over t plus 1 dt. So this is the y direction. So this is going to be 2 natural log, absolute value of t plus 1 from 0 to 5 for t. So that'd be 2 ln of 6 minus 2 ln. If I plug in 0, I get ln of 1. ln of 1 is 0. All right, so the x component is going to be 75 over 2. And then the y component is going to be 2 ln of 6. And let's just put them as decimals. 75 divided by 2. That's going to be 37.5. The y component is going to be 2 natural log. Remember, this is got to do it as vectors. This is going to be 3.58. And so the magnitude, okay, so the magnitude, or the magnitude of J is sometimes used for impulse. The magnitude of that is going to be Pythagorean theorem, because we've got to add them up like vectors. Got to add the x component squared plus the y component squared, right? And then square root of that is going to give me 37.7. And then we didn't have units on here, but they're Newton seconds, because you're doing, this is newtons, and then the time is seconds. And then the direction, just say it's the angle. We'll just say tangent of theta is equal to 3.58 divided by 37.5. And so the angle will be the inverse tangent, right? Just like we do with any other vectors. If we want to know the direction, we're going to establish an angle and then do that. So inverse tangent of 3.58 divided by 37.5, and that's going to give me about 5.5 degrees, like that. Okay, and so just be careful. That's probably the only thing to keep in mind is we're going to integrate when we're doing an impulse calculation if the force is varying over a function of time. And we got to treat it like vectors. So don't forget to do that. That's an easy thing to overlook.